Okay, we continue on looking at marginal distributions, and in particular, we're going to be looking now at marginal distributions of continuous random variables. So let x and y be continuous random variables with a joint PDF given by this expression. So we have seen this example before. This is the distribution where the sample space of the bivariate random variable x and y is the unit squared. Now, if we were in class, I would take out a sheet of white paper and I would take out a Sharpie marker. And on the overhead, I would draw a quick picture showing the sample space of this bivariate random variable. We really can't do that in this online context, but what I can do is show you, this is a picture, a graph here of the joint sample space of x and y, and I've created this on the TI-84. And so you can see here, so this point on the horizontal axis is 1, this point on the vertical axis is 1, and so this is the unit square that I've got shaded, and this is the sample space for the bivariate random variable x and y. Now, if you're interested, the way that I constructed or created this plot on the TI-84 is using this setup. So I entered this function you can see here for y1, and then I entered this command here, the shade command, which is on the draw menu. So look around for it if you're interested in creating a shaded graph. But this is the point is this is what the sample space is for this bivariate random variable. So what we're asked to do in this example, which is example 49, is to find the marginal PDF and CDF of x, and then graph those, and then also find the mean, the variance, the skewness coefficient, and the kurtosis of the marginal distribution of x. So our focus in this example, at least my focus in this lecture video, is to find the marginal PDF and the marginal CDF. I'm going to leave it to you to graph those functions and to find the mean, the variance, the skewness, and the kurtosis. Or I may give you the numerical values for those quantities, but I'm going to let you be the one to get the practice to go through and calculate them. We also want to find the marginal PDF and CDF of y, graph those functions, and as well find the mean, variance, skewness coefficient, and kurtosis for the marginal distribution of y. Okay, so the first thing we're going to do is to derive the marginal PDF of x. And so we're going to denote this marginal PDF by f sub 1. And note that since the space of x is the unit interval from 0 to 1, we know that this marginal PDF must be 0 for any value of x outside of this interval. So if x is less than or equal to 0, or if x is greater than or equal to 1, then we know automatically that this marginal PDF must equal 0. Now, for values of x greater than 0 and strictly less than 1, the marginal PDF evaluated at such an x is going to be obtained from the joint PDF by integrating that joint PDF with respect to y over the entire real line. So remember, this is just the definition for the marginal PDF of this first variable x, and so that's how we're going to obtain it. Well, this simplifies to the integral of 4 times x times y, integrating with respect to y over the unit interval from 0 to 1. And by the way, that's because the space of y by itself is from 0 to 1. Okay, now we can pull the 4 times x out of the integral because the 4 times x does not depend on the variable of integration y. And going through the calculations as we've done several times now, we're not going to spend much time on looking at that. But we get this expression for the marginal PDF of x, the values of x between 0 and 1, being equal to 2 times x. And so putting those two results together, the marginal PDF of x is equal to 2 times x if the argument to the function x is between 0 and 1, and it's 0 otherwise. Now, we've actually already found the mean and the variance of this function, and I believe we also found the skewness and kurtosis. We found that the mean was 2/3, the variance was 1/18, and 1 over 18. And like I said, I think we also found the skewness and the kurtosis, so you can look back in the notes and see what those were. And you might also just want to take the time to redo those calculations just to get some practice. Okay, now we're going to find the marginal PDF of y. We'll denote it by f sub 2. Since the space of y is the unit interval from 0 to 1, we know that the marginal PDF of y has got to be equal to 0 outside for any value of y outside of that unit interval. All right? For values of y between 0 and 1, we're going to obtain the marginal PDF of y by integrating the joint PDF with respect to the variable that we don't, or that we're not interested in, which is x. And we're going to integrate that PDF, that joint PDF, over the entire real line. When we do that, based on the definition of the joint PDF, that integral simplifies to the integral with respect to x from 0 to 1 of 4 times x times y. Okay? And now we can calculate this very simple integral, and it evaluates to the value 2 times y. So 2 times whatever the argument is, as long as that argument is between 0 and 1. So when we put those two results together, we get the fully specified expression for the marginal PDF of y. It's equal to 2 times y for values of y between 0 and 1, and it's 0 otherwise. And again, this is the same expression with just a different variable that we had for the marginal PDF of x. Okay, so and then we're not going to find the joint, CDF of the marginal distributions because we've already done that in those previous examples. So once we see these PDFs, we know that we've worked with them, and we know what the CDF is, so we don't have to redo that work. Now moving on to example 50, let x and y be continuous random variables with joint PDF given by this expression. And again, this is similar to the last example, but in this case, the sample space of the joint random variable is not the entire unit square. All right, it's the upper left triangular portion of the unit square. And in particular, let me show you, here I have another graph created using the TI-84. And so again, this region here is the unit square. The shaded region is the sample space for this bivariate random variable in this particular example. And here are the expressions that I used, and the expressions, the functions, and the command that I used to create that plot. So if you're interested, you can pause the video and copy that down. Okay, so that is what differentiates this joint PDF from the PDF in the previous example. The sample space is different. There's a constraint involving x and y. You see that x has to be less than y. So again, find the marginal PDF and CDF of x, find the mean, variance, skewness, and kurtosis. Again, some of these I think you'll see that we've already done, and so we won't replicate that work here. Then we also want to find the marginal PDF and CDF of y. Now, we're going to derive first the marginal PDF of x. And so again, as usual, we will denote the marginal PDF of x, which is the first variable in the joint distribution. And we'll denote this marginal PDF by f sub 1. Since the space of x is the unit interval, we know that if we evaluate this marginal PDF at any value of x outside that interval, we know that it's got to be equal to 0. For values of x between 0 and 1, we're going to integrate. We're going to apply the definition. So to obtain the expression for the marginal PDF at such an x, we're going to integrate the joint PDF with respect to the other variable y, and we're integrating over the entire real line. Now, notice that in this case, for a fixed value of x, what are the limits of integration for y? Well, let me bring up this picture again and see if I can kind of zoom in just a little bit. Okay, and so what we're going to do, we are picking a particular value of x between 0 and 1. And then we are going to integrate over the entire real line. So with respect to y. So going from minus infinity up to positive infinity. Well, that joint PDF is equal to 0 for any value of y at or below this point and at or above that point. The only values at which the joint PDF takes on a non-zero value for this fixed value of y right here is going to be from here up to here. Now, at this point, which we'll call, at this fixed point, this fixed value of x, x1, we'll call it x1. When we get the corresponding point on this equiangular line is, that point is x1, comma, y1, and those 2 points are equal because this is the equiangular line. So at that point, y1 is equal to x1. And then when we get up here, y1, the upper limit of integration is 6. And so that is why when we evaluate this, so I'm denoting this value of x1 by x. And so that's why this simplifies to the integral of 8 times x times y from y going from x to 1. And so then we can integrate in the usual way, and we come up with the expression 4x minus 4x cubed. So putting these two results together, we get the expression for the marginal PDF of x. It's equal to 4 times x minus 4x cubed for values of x between 0 and 1, and it's equal to 0 otherwise. Now, we've worked with this distribution before, and we found the values for the mean, the variance, the skewness, and kurtosis, so I've listed those values here. Okay. Now, we can also find the marginal CDF of x, and I'm really not going to spend any time on this because this is, when we looked at this distribution before, this was the starting point for this particular distribution. If I remember correctly, we were given the CDF, and we found then the PDF. So you can look at this, look at these calculations and make sure that we're doing it right. But once we have the marginal PDF, then it's a very simple matter to get the marginal CDF. Okay, now let's derive the marginal PDF of y. We'll denote it by f sub 2. Again, since the space of y is the unit interval, for values of y outside of that interval, this marginal PDF of y is going to evaluate to 0. For values of y greater than 0 and less than 1, right, we're going to obtain the expression for the marginal PDF of y by integrating the joint PDF with respect to x over the entire real line. Okay, so in order to do this, let me bring back up this picture here. And now we're integrating, we're picking a value of y, and we're specifically considering a point of a value of y between 0 and 1. So let's pick this value right here. Okay, and then we have to integrate with respect to x. Okay, and so this integral is going to simplify to the integral from x going from 0 up to this point right here. Now at this point right here, the point xy, x comma y, those two values are equal, and so x is going to be equal to y. And so that's why the upper limit of integration is y. All right, and so over that interval, the expression for the joint PDF is 8 times x times y. And we can integrate that, and I've skipped a few steps there, but that evaluates to 4 times y cubed. So putting these two results together, we get the fully specified expression for the marginal PDF of y being equal to 4 times y cubed for values of y between 0 and 1 and 0 otherwise. Next, let's derive the marginal CDF of y. And so denote that marginal CDF by cap f sub 2. Because the space of y is the unit interval, we know that for values of y that are less than or equal to 0, we know that this marginal CDF evaluates to 0. For values of y greater than or equal to 6, greater than or equal to 1, then we know that the marginal CDF must evaluate to 1. And so again, we get those two values for free, basically. But when it comes to values of y between 0 and 1, we've got to do a little bit of work. We have to integrate the marginal PDF. All right, and we're going to integrate from the marginal PDF with respect to this variable, dummy variable, the variable of integration we'll call v, from minus infinity up to the specified value of the argument, y. And so we end up getting y to the 4th power. So you can go through and do that calculation, and you'll get y to the 4th. And so the marginal CDF is given by, it's equal to 0. If we evaluate the CDF at any value of y less than or equal to 0, it's equal to y to the 4th for any value of y between 0 and 1, and it's equal to 1 if y is greater than or equal to 1. Now, let's go ahead and do the work to find the mean, the variance, the skewness, and the kurtosis. Now, we can use the marginal PDF of y to find a general formula for the expected value of y to the kth power. In other words, we can find a general formula for the kth raw moment. It's very easy to do here because of the nature of this distribution. And so the expected value of y to the kth power is, by definition, is the integral over the real line of y to the kth power times the marginal PDF of y. And this simplifies to the integral from with respect to y from 0 up to y. And actually, I need to use a dummy variable here. So I should be using v. So just in your notes, as you take these notes, or if this is in your notes, change the y here to the variable of integration to v. Okay? And then once we do that, then we'll get 4 over k plus 4. So once we have that, then it's very easy to find the first 4 raw moments. The expected value of y is 4/5. The expected value of y squared is 4/6 over, or 2/3. The expected value of y to the third raw moment, is 4/7, and the expected value of y to the 4th, which is the 4th raw moment, is 4/8. So again, we're just using this formula here. And once we have the first 4 raw moments, then we can use the expansion formulas, okay, which you, at this point, should have those formulas in your notes. Those formulas were given in a lab assignment, and we also talked about those formulas in a previous lecture, so you should have those formulas. And so we can use the first 4 raw moments along with the expansion formulas to get the second, third, and fourth central moments. All right, that's what we're after here, the central moments. And so once we have those, once we have the first raw moment and then the second, third, and fourth central moments, we can conclude that the mean of the distribution of y, the mean of the marginal distribution of y, is 4/5, or 0.8. The variance of the marginal distribution of y is 2 over 75, or approximately 0.02667. The skewness of the marginal distribution of y is this value here, negative 1.04978. And the kurtosis of the marginal distribution of y is 3.6964. So that is all we're going to talk about at this point regarding marginal distributions. We've seen an example a fairly thorough example involving marginal distributions and constructing marginal distributions from a joint distribution of discrete random variables. And we've also seen two examples of finding marginal distributions from joint distributions involving continuous random variables. So we've seen quite a bit here. Hopefully you're getting very familiar with this. The next topic that we'll be talking about are conditional distributions, but we're going to save that for the next lecture video.